Welcome to this presentation in the series, Electronics, the Story of One Human Lifetime by David Beams and Gary James. I'm David Beams, retired Associate Professor of Electrical Engineering. This presentation gives an introduction to semiconductor principles using basic physics with illustrations using simple analogies. If you pursue electrical engineering at the university level, you will study the foundational concepts in solid-state physics at a professional level, but you won't find that here. So let's call upon Nikola Tesla to state the questions we will answer in this presentation. What do we mean by a semiconductor? Why are silicon and germanium semiconductors? And how do we make useful electronic devices with these semiconductor materials? We'll begin by making a physical analogy to a material that is an electrical conductor, that is one that carries an electric current easily when an electric potential difference or voltage is applied to it. Let's take a cookie sheet and we'll place it flat, parallel to the surface of the earth, and we'll scatter some marbles on its surface. This is a representation of a material that has many electrons that are unbound or only weakly bound to any particular atom. If we tip the cookie sheet, we create a gravitational potential energy gradient. We note that all the marbles have run to the low end of the sheet. A marble at the upper end of the cookie sheet would be at a higher gravitational potential energy than a marble at the lower end. But the marbles are free to move easily, so they roll towards the lower end, toward lower gravitational potential energy. In the same way, when we create an electron energy gradient by applying an electric field to a material, and if there are mobile electrons under such circumstances, they will also move toward the region of lowest electron potential energy. Now we'll look at a different case. The cupcake sheet has been replaced by a sheet with cups or wells for baking cupcakes. Two marbles have been placed in each well. The marbles are analogs of electrons, and the cups are energy traps or wells formed by covalent bonds. This is a representation of a material in which the electrons are bound to specific atoms. Tipping the cookie sheet creates a gravitational potential gradient, but the marbles do not roll toward the lower end because they're trapped within their wells. Bound electrons cannot move in response to an electric field, just as these bound marbles cannot flow in the presence of a gravitational field. This is a representation of an insulator. Now let's turn to Tesla to explain what we're seeing here. This is the periodic table of elements, and the locations of germanium and silicon in column 4 of the periodic table are important. In a single crystal of pure silicon or germanium, each atom has a valence of 4 and forms 4 covalent bonds with its nearest neighbors. So now we will employ the cupcake sheet analogy to represent silicon. This model also applies to germanium, but we're going to focus on silicon in this presentation. So the locations of silicon atoms have been marked on the cupcake sheet. Each cup or well represents 1 covalent bond. Each covalent bond contains 2 electrons, represented by marbles. This close-up shows the silicon atoms and a covalent bond. Now let's look a little more closely at this cupcake sheet analogy of silicon. Marbles on the cupcake sheet have 2 discrete gravitational energy states depending upon whether they're on the surface of the cupcake sheet or in a well. They have a lower energy bound state where they are trapped in the well. They have a higher energy free state where they can roll easily. The 2 energy levels are separated by an amount equal to the mass of the marble multiplied by the acceleration of gravity and the depth delta H of the well. Only free marbles can move in response to a gravitational energy gradient. Similarly, electrons in the silicon crystal only have 2 available energy states. Lower energy electrons bound in covalent bonds are said to be in the valence band. Higher energy free electrons are said to be in the conduction band. And the difference in the energies between the two is called the band gap. And only free electrons can move in response to an electric field. Now we use the cupcake sheet to illustrate the situation in which a few electrons, have broken free of their covalent bonds. So here, some covalent bonds can be broken by absorption of photons, the photoelectric effect, or by thermal agitation, to which the crystal is constantly subjected. So there is a broken covalent bond, and there is another. Now, just as free marbles will roll easily in the presence of a gravitational gradient, free electrons move easily in the presence of an electric field. There are some free electrons, unlike an insulator, but there are fewer than in a conductor. So silicon is therefore neither an insulator nor a conductor, it's a semiconductor. Notice that the electron that has been freed from its covalent bond leaves behind an electron vacancy. This vacancy is called a hole. The free electron and the vacancy are called an electron-hole pair, or EHP. The creation of an EHP is a process known as ionization. Now let's bring some numbers into the discussion. Notice the band gap energies of silicon and germanium. And now look at the density of electron-hole pairs per cubic centimeter. The numbers look very large. In germanium, 2.4 times 10 to the 13th electron-hole pairs per cubic centimeter. These, by the way, are at 300 kelvins or 27 Celsius. And 1.45 times 10 to the 10th per cubic centimeter in silicon. Look at the electron-hole pair densities. They may appear large, but look at how they compare to the density of the atoms, the atomic densities, atoms per cubic centimeter. In germanium, the ratio is approximately 1 electron-hole pair for every 1.8 times 10 to the 9th atoms. In silicon, there is 1 electron-hole pair for every 3.4 times 10 to the 12th atoms. These numbers, by the way, these electron-hole pair concentrations are known as the intrinsic EHP concentrations of pure materials. We'll see that number again later, but we can see that ionization is a rare event. Now, would you suspect the probability of ionization would be connected to the band gap? Well, you would be correct. In fact, the band gap of a material determines whether it is a conductor, a semiconductor, or an insulator. By way of comparison, diamond has a band gap of 6 electron volts. Compare that to these numbers, and it is an insulator. Less ionization means fewer free electrons and greater resistivity, which is the material property having to do with how well or how poorly it can conduct electricity. Compare the resistivities of germanium and silicon here to that of copper. Look at the difference, many orders of magnitude difference. And look at their resistivities compared to glass. Now you can see why germanium and silicon are semiconductors. Well, let's look at what's happening in a semiconductor material at thermal equilibrium. Thermal agitation is producing electron-hole pairs. The electrons move randomly around the crystal. An electron in its random motion may encounter and recombine with a hole. The processes of generation and recombination are continuous, and they will balance at equilibrium. Now let's consider the conduction of electric current in the semiconductor. This battery provides an electron energy gradient or an electric field, and electrons will move toward the right side of this crystal, towards the lower electron energy, which is represented by the positive battery terminal. Now, some electrons moving to the right will recombine with holes, leaving a greater hole density on the left-hand side of the crystal. This makes it appear as if the holes are moving to the left under the influence of the electric field. Holes act as if they were themselves positively charged particles. We call them quasi-particles. Both negatively charged electrons moving to the right and positively charged holes moving left contribute to the flow of electric current in the crystal. The current in the external circuit is carried by electrons. Electrons are removed from the right-hand side of the crystal and re-injected into the left side where they recombine with holes in the crystal. Now let's turn back to the periodic table. Note the chemical element phosphorus in column 5. It has a valence of 5, which is 1 greater than the valence of silicon. Now we'll return to the cupcake sheet model of silicon, but we will replace a few silicon atoms with phosphorus atoms. This is a process called doping. Now notice where the phosphorus atoms have replaced silicon. The 5th valence electron of phosphorus cannot form a covalent bond with a neighboring silicon atom, and it becomes a free electron. Now let's let Nicola narrate or bring up the points of this slide. Dopants like phosphorus that produce excess free electrons are called donors. And this makes it an N-type semiconductor. Let's add 10 to the 16th phosphorus atoms per cubic centimeter to a crystal of pure silicon. This is actually only a trace amount of phosphorus. 1 atom of phosphorus every 5 million silicon atoms. Now, the product of free electron concentration and hole concentration is constant. It's equal to the square of the intrinsic electron-hole pair concentration in pure silicon. At 300 Kelvin, the square of the intrinsic electron-hole pair concentration in silicon is 2.1 times 10 to the 20th. So by adding 10 to the 16th phosphorus atoms, giving us 10 to the 16th free electrons, we drive the hole concentration down to 2.1 times 10 to the 4th holes per cubic centimeter. Now look at this. The resistivity drops immensely. Adding just 1 part of phosphorus for 5 million of silicon causes the resistivity to drop by a factor of 460,000. Okay. Let's ask Nicola to explain electric conduction in N-type silicon. Both holes and electrons can contribute to conduction of an electric current, but the density of electrons is far higher than the density of holes in N-type material. So the current in N-type material is almost entirely due to the motion of electrons. Let's go back to the periodic table again. Now let's look at boron in column 3, which has a valence of 3, which is 1 less than silicon or germanium. And now let's return to the cupcake sheet model of silicon, but now we will replace some silicon atoms by boron. We have doped the silicon crystal with boron. You can see where we've made the replacements with boron atoms. Boron can form only 3 covalent bonds with its silicon neighbors. Thus, adding boron to silicon produces a crystal with excess holes. Now let's ask Nicola to explain the electrical consequences of adding boron to silicon. Dopants that produce excess holes are called acceptors. It's an important term to keep in mind in solid-state technology. And semiconductors doped with acceptors are called p-type semiconductors. Now, we emphasize, again, this is only a trace amount of boron added to the silicon crystal. Each acceptor atom will contribute a hole. And you see what it does to the electron concentration. The hole concentration is driven up to 10 to the 16th per cubic centimeter. The hole concentration driven down to 2.1 times 10 to the 4th free electrons per cubic centimeter. Adding just 1 part of boron per 5 million of silicon causes the resistivity to drop by a factor of 150,000. An incredible change in resistivity for just a trace amount of boron. Now, Nicola can explain the conduction of electric current in p-type silicon. Both holes and electrons contribute to the current, but the density of the holes is far higher than the density of the electrons in p-type material. So the current in p-type material is almost entirely due to the motion of holes. Now, Nicola can clear up for us a common misconception. N and P don't mean negative and positive. They indicate the dominant type of charge carriers. N, electrons, P, holes. But both P and N-type materials are electrically neutral. This makes sense. Electrically neutral silicon and electrically neutral dopants will produce electrically neutral doped silicon. Many people think that P means positively charged and N means negatively charged. It's a little misleading. They don't. Now we form a P-N junction where P and N-type semiconductor materials are in contact. In practice, we don't form a junction by putting a P-type block in contact with an N-type block. We use this model to develop a simple explanation of the electrical behavior of a junction. Concentration gradients, large electron concentrations on the N side, large hole concentrations on the P side, will drive redistribution by diffusion. We will have holes diffusing from the hole-rich P side into the N side, and we will have electrons from the electron-rich N side diffusing into the P side. The N side then acquires a net positive charge as electrons leave, and holes leaving the P side give it a net negative charge. This charge layer creates an electric field that opposes diffusion, and any mobile hole or electron in the space charge region will be swept out, leaving this so-called depletion region devoid of mobile charge carriers. Now notice that the conduction band on the N side is at a lower energy than the conduction band on the P side. This energy barrier builds as diffusion proceeds, and it builds until it becomes large enough to stop further diffusion across the junction. Now we'll attach an external battery to the junction, and let's let Nicola explain what happens here. Pay attention to the polarity of the battery, negative to the P region, positive to the N. This battery increases the height of the energy barrier at the junction, and so no conduction takes place. We've only made the energy barrier between the P and the N sides higher by adding the battery with this connection. This connection is called reverse bias, and no current flows through the junction under these circumstances. But now we reverse the battery, the positive terminal of the battery to P and the negative terminal to N. And Nicola will explain happens here. Now note the battery polarity. The battery opposes the energy barrier at the junction, and diffusion resumes over this reduced energy barrier, and current flows. This connection is called forward bias. So the PN junction conducts under forward bias, but blocks current flow under reverse bias. It acts just like the Fleming valve. This simple structure is called a diode. The graph here shows electrical behavior under forward bias of two different diodes. The graph shows current on the y-axis versus voltage on the x. The first is of a general purpose silicon diode. And notice how rapidly the current rises with increasing voltage as we reduce the built-in energy potential barrier height. The second is a red light-emitting diode made with a composite semiconductor material, which is a mixture of gallium arsenide and gallium phosphide. Silicon and germanium are not the only semiconductor materials. Many semiconductor materials are compounds like gallium arsenide or cadmium selenide. Gallium arsenide phosphide has a larger band gap than silicon and accounts for the higher, what we would call the knee voltage seen here on the graph. LEDs emit light due to electron-hole recombination, and the wavelength of the light is determined by the band gap. Pure gallium arsenide emits infrared light. Pure gallium phosphide emits green light. Varying the ratio of gallium arsenide to gallium phosphide allows designers to tailor the band gap and produce a specific color of light. Now, Nicola will sum up this presentation. Basic understanding of semiconductor physics. Trace amounts of impurities profoundly affect the behavior of these materials. P-N junctions can rectify, but we really need a semiconductor device that can amplify like a solid state audion. So for solid state electronics to go to the next level, a new device, one capable of amplification, is necessary, and that takes us to the next chapter. The solid state revolution begins in 1947. Thank you for watching. The next presentation will continue with an introduction to the operation of our solid state audions, which were known as transistors.